Unit 3, Section 3. Today we're going to start talking about linear functions. All right, well, let's jump right in and talk about a few important details of linear functions. First of all, a linear function or linear equation is always in two variables, all right, x and y in this case. And it's an equation that can be written in this form of y equals mx plus b. This is known as the slope-intercept form of a linear equation. Now, it's called slope-intercept form because m, the coefficient on the x variable, represents the slope of that line, and b represents the y-intercept. And as you might assume, the graph of a linear function is a straight line. A linear function will have a constant rate of change, and this constant rate of change is known as our slope. You've probably learned slope formulas in previous classes. That is y2 minus y1 divided by x2 minus x1. Now this is called the rate of change or the slope of a line between 2 points x1, y1 and x2, y2. Another way we're going to think about this is the change in the y-coordinate divided by the change in the x-coordinate. A nonlinear function does not have a constant rate of change, and therefore it's not going to look like a straight line. Let's do a few of those examples here and you'll see what we mean. Does the graph represent a linear or nonlinear function? So this is just an eyeballing kind of question. You can see here we've got this slope that is continuing to change. As the line progresses from left to right, it's getting steeper and steeper. So this is going to be a nonlinear function. The graph in example 1b is linear. It is a straight line. It has a constant rate of change. And we can find out what that constant rate of change is by picking 2 points and using our slope formula, or counting the change in the y value divided by the change in the x value. It looks like this slope is going to be -1. In example 2, now we're not given the picture, but we're given a table of coordinates. We want to determine if this represents a linear or non-linear function. Well, remember, we can determine if it's linear if it has a constant rate of change. In other words, if it has a change in the y value over a change in the x value that is constant. All right, well, let's take a look here at 2a, and let's determine what our change in our y value is. To find out that change, we are looking at the movement between each of these y values. It looks like I'm adding 9 each time. All right, let's take a look at our change in our x values. It looks like we're adding 2 each time. So our change in our y value over the change in the x value is a +9 over a +2. And it's constant as we move throughout this function. So we're going to say that this is a linear function. Let's see what a nonlinear might look like. Our change in our y values looks like we're going up by 27. Then we're going to go up by 98. Then we're going to go up by a really big number, 218. All right, let's take a look at our change in our x values. We're going up by +2, +2, +2. So even though our change in our x is staying the same, our change in our y value over the change in the x value is not constant. In other words, it's not the same in between each one of these movements. So this is going to be a nonlinear function. All right, in example 3, now we're given the equations and asked to determine if these represent linear functions. So for equations, what we're looking for is to see if we can fit it into y equals mx plus b. On our first one here, y equals 7, this actually does fit into y equals mx plus b because our m value can be 0. So this is going to be a linear equation. Our next one involves the square root of x, and that is going to be nonlinear. And you can see that our next one here, y equals 2 to the x, is going to be this exponential function, and that's not going to be linear either. All right, now we have y equals 3 divided by x. So when our x appears in the denominator, this is also going to be a nonlinear function. All right, next up we have 2x equals 4y plus 1, we can maneuver the 2x over to the other side and then divide both sides by 4, so we would end up with the equation y equals negative 2x plus 1 all divided by 4, which is a linear function. We can write this as negative 2/4 x plus 1/4. That fits into the y equals mx plus b format. All right, our next one here is x squared plus 7 equals y, which, because it has an exponent on it, is not going to be a linear equation. So we're going to write that one over here under the nonlinear. And finally, we get y equals x divided by 3. And now you might be thinking this y equals x divided by 3 is the same as this y equals 3 divided by x. However, you can rewrite this as y equals 1/3 x plus 0, which does make it a linear equation. All right, in our previous section of notes, we talked about a discrete and continuous graph. Well, now let's talk about a discrete and continuous domain. A discrete domain is a set of input values that consists of only certain numbers. And when we write that domain, we're going to write it with an open brace, and we're going to list each one of those values. So we have -4, 0, 2, and +5. And we'll close that up. So this is a discrete domain. We're going to list each individual integer here that's listed with a closed circle. And now to contrast that with a continuous domain. A continuous domain here, you can see, is all of these values between -4 and 5. And this is a set of input value that consists of all the numbers in that interval. And the way we're going to write this is using interval notation. We want all the x's that are greater than or equal to that minimum amount, which is -4, and they have to be less than or equal to that maximum amount, which is +5. So this notation, this interval notation, is quite a bit different than the discrete notation. All right, our final few examples just want us to graph some linear functions. The linear function y equals 1.25x represents the cost y in dollars of x bottles of orange juice. Each customer can buy a maximum of 5 bottles. Graph the function below and answer the following questions. All right, so let's graph this and think about your different inputs and your different outputs. Your inputs, remember, are your domain. So I could purchase 0 bottles of orange juice. I could purchase 1, 2, 3, all the way up to 5 bottles of orange juice. Now keep in mind, these are just whole numbers. I cannot purchase 1.5 bottles, 2 1/3 bottles. So this is a discrete domain. It is not going to be continuous. So when it comes to graphing, we are going to graph by putting in our inputs, our x values, and figuring out what our outputs or our y values are. If I purchase 0 bottles of orange juice, my cost will be 0. 1 bottle, it will be $1.25. 2 bottles, it will be $2.50. 3 bottles, it will be $3.75, so on and so forth. So when it comes to plotting this, we are going to make sure that we plot these discrete or dots on our xy plane. All right, so here we go. We got 1 over 1.25, 2 over 2.5, 3 over 3.75, 4 over, and it's going to be $5, and then finally 5 is going to be $6.25. And this is what the graph of this linear function would look like. All right, our last example, your friend runs at a pace of about 5 miles per hour. Graph the function below and answer the following questions. Now for this one, our domain is going to be continuous. And the domain here is going to represent the number of hours for which that person is running. So we're going to say our x can be anything greater than or equal to 0, because you could run for 0 hours, or you could run up to 10 hours, I guess, if you're physically fit enough. If we take a look at our y-axis, we got our number of miles. So we're going to say y is equal to 5 times x. Remember, this is just our handy little formula, distance equals rate times time. All right, so let's plot a few different points here. If I run for 1 hour, I will have gone 5 miles. 2 hours, it will be 10 miles. 3, it will be 15. Now I'm just plotting these points right now, but keep in mind that this is a continuous line. So I actually do want to connect all these dots and make it a nice straight line.